This chapter is an introduction to chemical equilibrium. Chemical equilibrium is a real hard concept in AP Chemistry. We're going to cover 3 chapters of it. 15 is pretty easy. 16, 17 is where it starts getting harder. Chemical equilibrium happens where you have 2 reactions occurring. One is a forward reaction and one is a reverse reaction, and they occur at the exact same rate. Not all reactions have equilibrium. Equilibrium only happens whenever you have reactions that are reversible. Reversible reactions are symbolized by this right here, a half arrow going one way and a half arrow going another way. Now the word processor that I use to make your notes can only make this symbol right here, and so this is the one that's used in your notes, but that is not the correct symbol. The correct symbol is this symbol right here. This is the one that you need to use when you answer your questions. This is the right symbol for chemical equilibrium. The way that reversible reactions work is they're composed of 2 different reactions happening at the same time, a forward reaction and a reverse reaction. So for example, in this reaction right here, you have N2O4, which is a colorless gas, decomposing into NO2, which is a brown gas whenever you heat it up. You have a forward reaction, the reaction that goes from this direction to this direction, but you also have a reverse reaction in which NO2 is reforming into N2O4. Alright, reactions that can do this, that have a reaction going from here to here, but also a reaction going from here to here, these are equilibrium reactions. Now, since in these reactions you don't really have products and reactants, because you can have one side turning into the other side or the other side turning into the other side, we tend to use the terms left and right to describe what direction the reaction is going the most. Alright, so if you're going this way the most, you're forming a whole lot of this stuff, we tend to say that the reaction lies far to the right. Or if you're going the other direction, then making a whole lot of this, then we say the reaction lies far to the left. You want to make sure that you are pretty familiar with the terminology involved here: forward reaction, reverse reaction, equilibrium lying to the right, equilibrium lying to the left, because you're going to be using this terminology a lot. Let's say that we're starting at the beginning of this reaction right here with a whole bunch of this N2O4, and when it starts decomposing. The second it starts decomposing, the rate of the forward reaction starts reducing, because we know that when the concentration of N2O4 goes down, the rate's going to go down as well. But as the concentration of this starts to increase, the rate of the reverse reaction starts to increase. So at some point, what's going to happen is the 2 rates are going to equal one another. And when these 2 rates equal one another, what we can do is we can see a ratio that occurs between these 2 rates. And the ratio of these 2 rates, and in particular the ratio of the 2 rate constants, is something that we call an equilibrium constant. And equilibrium constants are very, very important in equilibrium. So let's take a look and see what our equilibrium constant is and what it can be used for. I'm going to skip through this, except to show y'all guys one thing. We've seen this chart before. We saw this with rates of reaction, and we talked about when it levels off right here. At that point, that's when equilibrium has been reached. Notice that you don't have a 0 of anything. Just at that point, you have a certain amount of H2, a certain amount of NH3, a certain amount of N2 that has been made, and it's going to stay at about that. When that happens, that means that the rate of the N2 and H2 reacting to make NH3 is equal to the rate of NH3 reacting to make N2 and H2. So we still constantly have N2 and H2 making NH3. We still constantly have NH3 decomposing. It's just occurring at the same rate as one another. Alright, so let's take a look at the equilibrium constant and see what's going on here. Here we've got a balanced chemical equation right here. This balanced chemical equation represents our guys on our left. We'll go ahead and call them our reactants for right now, and then our guys on our right, we'll just call them products. Now, what I can do is I can put these into an equation that is going to help me find the equilibrium expression. Here's what the equation looks like. Now, this is a really important equation. The equilibrium expression is K. It's going to be equal to the concentration of your products, the guys on the right here, divided by the concentration of your reactants, the guys on the left here, taken to the power of the coefficients that are in the equation. This equation will allow you to calculate the value of the equilibrium coefficient, and it's a really important equation that you're going to be using a lot. Notice that the things that are in the equation are concentrations. That means molarity, and that means, guys, solutions. What that also means is you can't have solids and you can't have liquids in an equilibrium expression, because solids and liquids are not solutions. You can have gases. We'll get to that in just a little bit. K is our equilibrium constant. K can change depending on your coefficients, it can change depending on your concentrations, and it can also change depending on temperature. We're going to see exactly how it depends on temperature at the end of the chapter. This symbol here, our X in brackets, represents the concentration of the chemical species when it has reached equilibrium. So it's not its initial concentrations, it's its equilibrium concentrations. If I was going to do the equilibrium expression for the reverse reaction, it'd be pretty much the same thing, only you're switching your products and your reactants. And since it's the same thing except inverted from this thing right here, that means that your value for K is going to be the inverse of this value of K here. So the value of your equilibrium expression for your reverse reaction is the inverse of your value of your equilibrium expression for your forward reaction. Now, like I told you before, we do not include pure liquids or pure solids in equilibrium expressions. We do use solutions, and you can also use gases. The reason why is because the concentration of gases is directly related to their pressures, and so you can use pressures to do concentrations of gases. All right, so for example, if I was looking at this reaction right here, and I wanted to do the equilibrium expression for it, it would look like this. This would be the equilibrium expression for concentration. However, if I was asked to solve for Kp, this is the equilibrium expression for pressure. This is going to look a little different. When writing an expression for Kp, you use partial pressures instead of concentration. So I would do the partial pressure of NH3 squared over the partial pressure of H2 cubed times the partial pressure of N2. You use parentheses instead of brackets. You use P's, all right, instead of concentrations. So when you are asked to write the equilibrium expression for a Kp value, keep in mind the differences between that and a regular K value. There is a relationship, direct relationship between Kc and Kp. It's this one right here. You need to make sure you have that memorized. Kp is equal to Kc times R times T in Kelvin times your change in number of moles, where change in number of moles is the difference between the coefficients in your products and the coefficients in your reactants.